Hello and welcome back to Calculus 1, section 4.4, optimization. Probably my second favorite, right after related rates. And there's a lot of useful engineering and business-related stuff here. These are obviously all word problems, applied problems. And this section shows how important and how powerful calculus is. We are going to start this section by first working out some meaningless stuff, and then we're going to take a look at real good examples. So the idea of the section is to use the idea of min and a max to optimize functions and problems. We know that we learned in the previous sections that we are setting the first derivative equal to 0 to find min and a max. So now in optimization, we will see that once we write mathematical model and differentiate it, it's automatically equal to 0, which is the same concept, and the equation that it's left after differentiation, once solved, gives us min or max values. So first we take a look at these exercises just to kind of figure out what's happening. So say minimize the product of x and y given the constraint x plus y equals to 10. If you are supposed to minimize the product, this sentence here is translated as xy equals a minimum. And that is known as the objective function. So objective of this problem is to find x and a y so that their product is minimum. The other equation that is given to us is called the constraint. Function. And now look what you have. You have two equations and two unknowns. You will solve this equation, let's say y equals 10 minus x, and plug in to get x times 10 minus x equals a minimum, which further is equal to 10x minus x squared equals a minimum, which now we can use to take the derivative. Note that I couldn't take derivative earlier because I had two variables, right? I couldn't take derivative all the way on top where it said xy equals the minimum. We need to differentiate that equation, but we can't until we get rid of one of the variables. And that's where the constraint comes in. So constraint will eliminate the other variable. So once we have this, now I have 10 minus 2x equals to 0. Because minimum is some value, right? Minimum is some value, maybe 12, maybe 12.6, maybe 37. So minimum is some number, and when you differentiate that, you get 0. And look, you can find that x is equal to 5. And now, you also have equation over here which says y equals 10 minus 5 is another 5, and we get x equals y equals 5. Now, if you want to verify that this calculation did give us the best values for x and y, so we have a minimum, remember what you had. The constraint was that x plus y has to be 10. So this is the solution. We're done. Now we're just like checking or checking the answer. Do what? Oh yeah, Max, you're right. Wait, what did I write wrong? Ah, it's x squared times y. That's okay. I'm just gonna change this into a max. It's not a big deal. Just change max throughout and the problem is right. Nah, not a big deal. I mean, it is a big deal, but it's easy to fix. So I just need to change a few of these values here. And you know what? I would discover that in like 30 seconds because I was about to do this. So we know that 5 plus 5 is 10, right? And we get 5 times 5 is 25. Now, what other combinations would make 10? Let's say 6 and a 4, right? Because 6 plus 4 is also 10. But look, 6 times 4 is 24. Give me any two numbers other than 5, 5 that add to 10. 7 and 3. Right? So 7 times 3 is 21. And then 8 and 2 also add to 10, but 8 times 2 is 16. So you can use decimals, you can use fractions, you can use whatever the hell you want, including e's and pi's. Doesn't matter how complicated you want to make it. There is only one solution under the sky that will give you a max value for the product, and all other combinations of numbers that add to 10 will give you less than that. So that is the power of calculus. It will zoom in on that absolute max or the absolute mid combination value, right? That cannot be beaten by other values. So now let's see some of the so it says find the minimum sum. How about that? Minimum sum. Find positive numbers x and y whose product whose product is 50. So you want to find the minimum sum. So find x and y whose product is 50 and you have a minimum sum. So how would you write the minimum sum equation? Minimum sum. X plus y is equal to minimum. So that's your objective equation. Objective function. And then whose product is 50? X times y is 50. Always the same deal. Two equations. One is going to be objective that has min or max in it. The other one is constraint. constraint function, constraint equation. You always solve that one for either x or y, and then you plug in. So you get x plus 50 over x is equal to a min. And once you have the objective equation with only one variable, you hit that with the derivative. So square root of 50, we are going to have answer plus and minus 5 root 2. But we know we can't use minus because the problem said positive values. So just 5 root 2. And then we have that y is equal to 50 over x, which is 50 over 5 root 2, which is 10 over root 2. We rationalize that, and we get another 5 root 2. So again, we got x equals y equals 5 root 2. Again, same values. Are they always going to be same values? The answer is hell no. It's important to read the question carefully and set up equations. After that, procedure is really straightforward. So if you are able to get the equations together, you guys can solve the rest. So here are some of the favorite problems that show up pretty much all the time. Farmers' problems. We start is that, let's say, farmer has 2,000 feet of fence. So we're going to start there. Farmer has 2,000 feet of fence. Let's go with problem number 1. What is the largest rectangular area that can be enclosed with 2,000 feet of fence? Well, it's a geometry problem, right? We know rectangular area looks like a rectangle. We call this x, we call this y. What is the largest rectangular area that can be enclosed? So how do I write that as a mathematical sentence? xy equals max. Nice. So we are maximizing area. That's our objective. Now, what do I do with these 2,000 feet of fence? Why? Why? Perimeter. It's a perimeter fence. So 2x plus 2y equals to 2,000. And that's our constraint. Just think about the words, right? You see that you're operating under constraint, which is 2,000 feet of fence. You don't have any more, right? You want to use it all. So now, once you have this, procedure is again the same. From the constraint equation, x plus y equals 1,000. Y equals 1,000 minus x. Plug in. We have x times 1,000 minus x equals to a max, which is 1,000x minus x squared equals a max. Hit it with a derivative, because now it only has one variable. We get 1,000 minus 2x equals a 0. X equals 500. And then again, y equals 500. So the largest area that you are going to get is 500 feet by 500 feet. And you will use up all 2,000 feet of fence. So we actually get a square. 500 by 500. Problem 2 is more interesting. Same farmer, same fence, everything is the same, except now it's adjacent to the river. So he only needs to enclose 3 sides. Put some salmon in here. You have them as pets? Oh, for dinner, okay. There's some salmon. Oh, if the salmon is swimming to the right, which way the water goes? Yes, depends on it. Depends on the season. Yeah. Yeah, I'll practice drawing the bear next time. The bear would be in the water as they jump.
Is it the same amount of fence?
Yes, 2,000. So how would you set this up? Again, we want the maximum region. Anyone? Yes? Very good. So now we still have xy equals to a max. We want the maximum area, but the perimeter changed equation. So that will change our calculations. We see now x is equal to 2,000 minus 2y. And now when we plug that in, hit it with the derivative, we see it's different. Now observe that I'm taking now derivative in respect to y, whatever the variable is there. So that's 2,000 minus 4y equals 0. Hey, y is 500. But x is 1,000. So it's no longer a square. So now we have 1,000 by 500 feet. Earlier we had 500 by 500. Obviously we can enclose more area because we are not using fence on one side. All right, one more. Let's say the farmer wants to enclose, make 3 bins. Cabbage, rabbits, and tigers. You have to separate these from each other, right? Because Rabbits are going to eat the cabbage, tigers are going to eat rabbits, so you have to put them in separate bins.
We're doing area, not
Wait, what happened?
What if they're friends? What if they're not people? Just like
I said tigers and rabbits.
yeah, just gonna like assume that
And no one is cabbage's friend.
What's that?
I hope, because that would be a serious condition. You see someone walking, talking to a cabbage, like, all right. So, no friends here, all right? Just mortal enemies. We want to separate cabbage from rabbits from tigers. Everyone gets their own bin. We have no issues.
the tigers will eat the rabbits, and the rabbits will eat the cabbage.
Exactly.
What's different?
No friends.
Again, 2000.
Again, 2000. Let's see. So I'm going to erase the CRT and put, how many Y's do we have? 4 Y's. And how many X's do we have? 2 X's. So what is my area equation for maximizing? No, objective equation, the max. X, Y equals max still. Nice. And what is the other equation, the constraint? 2x plus 4y equals to 2000. I'm just going to put 3 dots here because it's the same calculation. Now, you could have all other configurations that you can possibly think of. Let's say you want to do, you know, maybe half this way and half this way, like this. Put the cabbage here and the rabbits on the outside, right? Rabbits need more room to run. You can do all of these things. So this would be x over 2, y over 2, the entire x, entire y. You can play with configurations. You can have 4 bins. So there are ways to work with this. So over here, equation would be still xy equals the max, but then your area, your perimeter is 2x plus 2y plus, you have x over 2 plus y over 2 equals to 2000. And I put 3 dots again because add common denominator, figure things out, plug in, take the derivative. So all of these problems are constantly the same. What I want to talk about in the last 20 minutes is to show how powerful this stuff is. It's a business problem. Let's say we have the oil rig. This is the shore, this is the sea. You have the oil refinery right here. And this is close. There is no need to, you know, ship the tankers and so on, back and forth. What you could do is build a pipeline. So say this is 4 miles, and say this way 6 miles. So what you could do is you could build a pipeline through, and what we know is that building pipeline underwater is much more expensive than building pipeline on land. That should be common sense because you have to work underwater. Welding and everything is harder, much harder underwater. So say that 1 mile on land for pipes, so pipeline, 1 mile on land is, let's say, maybe $100,000, and 1 mile underwater maybe $500,000, whatever. So we do not need calculus at all to figure out how much we need to get these straight distances. This could be route. So let's go with purple. Purple, route number 1. Very simple. What's the cost to build a pipeline? You have 4 times $500,000, that's underwater, plus 6 times 100,000, and you have 2,600,000 to build the pipeline that goes on the coast, right? And then underwater, the shortest distance, because that's the most expensive, right? And then you have the blue one, blue pipeline, number 2, which is all underwater. But that's the shortest distance to the oil rig, from the oil rig to the refinery, shortest distance. Well, we have to use the Pythagorean Theorem to figure out the distance d there, right? So I need to go and say it is going to be 4 squared plus 6 squared, and everything is underwater, so I have to multiply that by 500,000, which is the amount. So now we have 16 plus 36 is 52, square root of 52 times $500,000. $3,605,551.28, please. Very important on the 3.6 million. Those 28 cents. So clearly, the purple one is much better, cost efficient, right? So $1 million savings, right? Can we do better? Calculus, yes. So let's say you are sitting at this business meeting, you're listening to this, and you have this, algebra student proposing the purple one because it's a savings of $1 million. And then you go, but hold on. What if I go a little bit and then cut through? Would that be a better mentioning color? Look at that. The color power. So would this be better version? If I call this distance over here x and call this one over here d, the cost would be x times 100,000 plus d times 500,000 And if we are to use calculus, my claim is that whatever the red cost comes out to be will be less than all the others. All right, so let's see. First of all, I have to figure out what I need to minimize. I want to minimize this equation. I want this cost to be minimum. And as you can see, I have two variables there. So I have to use the fact over here that this distance here is 6 minus x. And if you use that 6 minus x there, you can use the Pythagorean theorem to figure out that d is the square root of 6 minus x squared plus 4 squared, because it's the right triangle. And then you can solve this square root here as 36 minus 12x plus x squared plus 16. So finally d, which is our constraint equation, d is equal to the square root of 16 and 36 together is 52 minus 12x plus x squared. Plug in, as usual. All of the problems are the same. And we have 100,000 x plus 500,000 times the square root of 52 minus 12x plus x squared equals to a minimum. And now hit that with a derivative. From there you calculate x, bring back x here to calculate your d, put your x and d in the minimum equation, and you will show that the values you picked, the x and the d, would give the smallest cost. Now we just need to see how much are we saving, right, with this calculation. So what do I have? The derivative of 100,000 x over here is just going to be 100,000 plus, and now we have to take the derivative of this. So you know that the square root is going to be 1 over 2 times square root, which cuts this into 250 times 1 over, not 1 over, sorry, the derivative on the top is 2x minus 12 times the square root of 52 minus 12x plus x squared equals 0. And all we need to do is to solve this. Now this might look intimidating, but it's not a big deal at all. Move 100,000 to the other side, divide by 25, so we get 2x minus 12 divided by the square root is equal to negative 100,000 divided by 250,000. You can factor out the 2 on top, get x minus 6 divided by the square root is equal to the negative, and this is going to be 10 over 25 when you cancel, and then you can divide by 5, so 2/5. And now 2's will cancel. Such an easy problem, as you can see in calculations, I mean. And now we cross multiply. So I have 5 times x minus 6 is equal to the negative square root of whatever we had. It was 52 minus 12x plus x squared. Square both sides to get rid of the square root, we get 25x minus 6 squared is equal to minus dies and now we get, when you square here, we get 25x squared minus 12 times 25x plus 25 times 36 minus x squared plus 12x minus 52 equal to 0. I move everything to the left. 24 x squared. Now I have that's actually easy because it's 25 times 12 and then it's 12x, so that's 24. That's 144 times 2, 288. That was easy. And then 25 times 36. Steal from here, steal 4, because 36 that's 4 times 9, so it's 900. Minus 5 is 848. These numbers lined up nicely. So, but now we're out of luck because, well, we're not, because we can divide by 4. Right? So 200, that's 50. We can still divide by 2. I'm lazy to go. Yeah, this one doesn't divide, so. All right, now use quadratic equation.
Yeah, Professor, I think with that last one, 848 divided by 4, it should be 212,
Oh.
right?
Yeah, it should be 4. Yep. Should be 424. So it should be.
It should be 212. 212 because we divided 848 by 4, not by 2.
Wait, I had it right.
484.
242.
No, it's 212.
That's what.
Oh yeah, 212. Yeah. 212. And then when you divide by 2, you get 106. Oh, okay. I see. Great. So 36 squared minus, I get 24. So 36 plus square root of 24 divided by 6 is 6.82, or if we use the same,
Professor, how'd you jump to 6.82?
36 plus square root of 24 divided by 6.
Couldn't you just simplify it to 6 plus minus 2 root 6?
Yeah, but you still need the decimals.
Yeah, for the actual
Mm-hmm.
application of the problem.
And here are your two x's. Just have to figure out which one gives you the smaller price. Now you bring, I'll call them x1 and x2. So figure out your d1 and d2 from this equation. And then you plug x1 d1 in equation, see the cost, and plug x2 d2. So I strongly encourage you to finish off this problem at home. Let me find d1, and then you just find d2 the same way. So d1, we have equation that connects d and x right here. This is important equation. So d1 will be 52 minus 12, okay. 12 times 6.82 plus 6.82 squared, right? And that's going to give you a number. I get 4.08. So that is a pair that I put in a cost equation. And then we repeat the same thing for D2. $5.18. Yeah, and obviously you get the same value. Good. So what's this? So what's the smaller cost?
How can you put the same amount?
The triangle. Because if it's up above, it's symmetric. So we'll use 518. So if you put 518 and 408, we should have the lowest prices. If all calculations worked out fine without any mistakes, that should be it. I was rushing a little bit, so I'm hoping that all of this was. I get $2.5 million. So with these, the price would be, so cost would be equal to 2,558,000 if we use these values. And look at the other one. So this is 2.5. The other one is, so it's less than the purple one. And this is where you make money. This is the contracting jobs. Well, we're going to do a few more problems tomorrow, and then I will upload the notes. I won't be streaming the other 3 or 4 problems we do, but I will write them here on the same lecture notes, and then I'll upload the notes.
Hey, Professor, before you cancel the stream, do we want to talk about when the exam is going to be, or when do you think we'll finish chapter 4 by? Because it's up.
We'll be done by Thursday, definitely. Yeah.
So
Yeah, we'll talk.